In this video, I will explain how intrinsic forces can be used to generate and tune the strain of electrocatalysts. Strain is a measure of deformation in a material body. Tuning surface strain is a powerful strategy for tailoring the reactivity of electrocatalyst. For the catalytic reactions in fuel cells, a 1% compressive strain can enhance the performance over 300%. But traditionally, strain is imposed by exerting external forces through catalyst support interfaces, which may encounter many stability-related issues. This science paper introduced a strategy to generate and tune the strain without external forces and interfaces. To explain fundamental principles behind, let's imagine two people are playing tug of war, but instead of standing on the ground, they are on a spring. When they pull the rope, their hands will exert two tensile forces in the opposite directions. At the same time, their feet will exert two compressive forces on the spring, also in the opposite directions. Then the spring will contract and generate compressive strain. If they use a thinner spring, the magnitude of strain will increase. Tug of war can be played by 4 people. In this case, any 2 nearby people are playing tug of war with each other, and there is a compressive strain generated on each spring. If they use thinner springs, then the magnitude of a strain will increase. Tug of war also can be played by many people. This is analogous to the atoms on a metal surface. There are attractive interactions between any 2 nearby atoms, which leads to the tensile surface stress. The magnitude of the surface stress is on the order of a Newton per meter. For example, the surface stress of a palladium-111 surface is about 2.5 Newton per meter. As the thickness of an atomic layer is about 0.25 nanometer thick, or 2.5 times 10 to the minus 10 meter, this surface stress can induce a surface pressure on the order of 10 to 10 Pascal or 10 to 5 atmospheric pressure. This huge pressure provides a strong driving force for the compression of the lattice to reduce the surface energy. While this surface pressure has little effect on metals with macroscopic thickness, it can lead to generation of strain on 2-dimensional nanosheets, as nanosheets are analogous to springs. If we decrease nanosheet thickness, analogous to using thinner spring, the magnitude of spring will increase. Based on this strain thickness relationship, we use the density functional theory calculation to design a series of nanosheets. We have synthesized palladium nanosheets, which vary from 3 to 8 monolayers in thickness and have compressive strain from 2% to 1%. Our electrochemical test indicates that these nanosheets are highly active for fuel cell reactions, in agreement with the computational predictions. For example, the 5 monolayer nanosheets can enhance the catalytic activity up to 50 times in comparison with the commercial catalysts, thus generating and tuning the strain of electrocatalyst by utilizing intrinsic surface stress is a promising strategy to boost the performance of fuel cells and other electrochemical devices.